Welcome to Dr. BT's Chemistry Essentials, A-level chemistry made easy. In this video we're going to be looking at the electrophilic substitution reactions of benzene and focusing in on the two functionalizations of putting a nitro group on, and that's called nitration, and then putting a halogen group on, and that's halogenation. So first let's just focus on what is actually going on in nitration and halogenation. So we're taking a benzene ring as our starting material, and what we're going to be doing is with this reactant we're going to be introducing a nitro group, and this process of introducing this nitro group is called nitration. And the way in which this happens is the hydrogen that existed at the position that the nitro group now occupies is actually substituted. So substituted means swapped, and we can see this hydrogen is now here. Okay, so this is going to obviously combine with something else to form a byproduct, but in replace of the hydrogen is this NO2 group here, the nitro group. Now the mode at which this happens, or the type of mechanism, is known as electrophilic substitution, and nitration is one of the examples of these. In fact, all the transformations and reactivity when we're dealing with benzene undergo electrophilic substitution. And this is opposite to the year 1 alkene chemistry, which is also a pi system, that undergoes electrophilic addition reactions. Now later in the video, we're going to look at the actual mechanism for this electrophilic substitution. But just for now, we're going to look at the reagents and conditions that we need and the byproducts of each of these transformations. So focusing back on the nitration here, to get the nitro group in, the reagents and conditions that you need for this reaction are concentrated nitric acid, which is obviously the source of the nitrogen and the oxygen, but this alone won't work. We need to pair that up with concentrated sulfuric acid. And if we just want mononitration, so the introduction and substitution of only one hydrogen for one nitro group, then we need to have this at anything around 50 degrees. Anything higher than this will give multiple substitution. So it's really important to remember these, have them on a flashcard or something with this transformation. The only thing that they can make difficult here is if this benzene is substituted with other things, but your job is to find the pattern and see that a nitro is being introduced, and then you'll be able to come up with these reagents and conditions for that. Now, this hydrogen doesn't just sit solely on its own. When we look at the mechanism later, we'll see that the byproduct here is water. Now, the other two transformations that we're going to be looking at in this video is the introduction of bromine, and this is called bromination. It's not surprising that this too is an example of electrophilic substitution. And the other transformation we're looking at in this video is where we substitute the hydrogen for a chlorine, and this is called chlorination. In order for this to happen in bromination, we need the reagents, bromine, and then we need some sort of what's known as a halogen carrier. Now you'll notice that the halogen carrier has the same halogen attached to a metal. So here we have iron tribromide, or you could use aluminium tribromide. And the reason we need these halogen carriers is because they create the electrophile. So obviously we've got bromine here. We need an electrophilic version of it, and we'll look at that when we look at the mechanism next. But just to remember, you need bromine and one of these halogen carriers, and you need to memorize these as your set of reagents. Now the conditions for this are reflux, and we're remembering that once we add this bromine on, we have substituted the hydrogen, so this is going to be a byproduct. And the other bromine of bromine that hasn't been added in onto our benzene ring combines with the hydrogen to form hydrogen bromide. Furthermore, the conditions that are required for this transformation is temperature of reflux. And finally, chlorination, very similar. We're going to use chlorine, so Cl2, as our reagent, and that's going to have the halogen carrier either FeCl3, so iron trichloride, or aluminium trichloride. And once again, only one chlorine is added on and substituted. Substituting the hydrogen, so we're going to have hydrogen And the second chlorine combines with this to form hydrogen chloride, or HCl. So our attention now is going to focus on what is actually happening in these processes of substitution, and what are electrophiles in each of these different cases of nitration, bromination and chlorination. So with this mechanism, we're going to start with benzene, and we're using the delocalized model of benzene. Remember to watch the video on calculate versus delocalized model if you're unsure about what we mean by that. And we're going to react this with our generic electrophile. So our electrophile is going to be given the symbol E for electrophile, and plus because that's the charge on the electrophile. Now benzene has a pi system, and so it has lots of electrons. And these are obviously negatively charged, and so there's going to be an attraction between this area of electron density and this electron deficient electrophile. So electron deficient, it doesn't have enough electrons, and that's shown through this charge of the plus. And so obviously in chemistry, opposites attract. So what happens is the electrophiles from this electron-rich environment are then going to form a new bond with this electron poor or deficient environment. And remember, we showed the movement of electrons, and it's a pair of electrons with a double-headed curly arrow. So they're coming out of the ring and they're attacking the electrophile. So if we make the substitution, the overall substitution happen at this site, at this carbon, then we formed a new bond in this step to the electrophile at this carbon here. Now, obviously, there has been a temporary disruption of this delocalized pi system, and we need to show this in our diagram. Now, because this is the carbon that's formed a bond to the electrophile, the ring system will not extend to cover this carbon. So instead, what we do is we start from this carbon next door to it, go all the way around, and make almost a horseshoe shape, and it has to stop at this carbon here and this carbon here, leaving the carbon that has formed the new bond as not being part of the ring system. Now, because electrons have been taken from this ring system, it's now positively charged because they are away from the system, and so we end up with this positively charged intermediate. Now, two parts of this mechanism show us what's going to happen in the next step. First of all, we know that benzene has a really stable delocalized pi system that it wants to reform. So we're going to close this gap here. And secondly, from the title of the mechanism, it's a substitution. And right now, what we've all just done in this step is just added in the electrophile. So we're going to have to remove this hydrogen, and in the same breath also reform the pi system. So what's going to happen is, in this sigma bond between the hydrogen and the carbon, the pair of electrons that are involved in this bond are going to be used to push back into the pi system, thereby breaking this bond and freeing up the hydrogen to go elsewhere. And so if we draw this process, so curly arrow to show this going back into the ring, and again ensure that your curly arrow goes into the actual cyclic structure. This then allows this hydrogen to be free, therefore leaving only the E carbon bond and a hydrogen as a byproduct. And that's why in the reaction schemes we've seen, it's always either hydrogen bromide, hydrogen chloride, or H2O in the form of nitration as your byproduct. So this generic mechanism can be used to explain all the different types of electrophilic substitution that you're going to see. In this video, we're looking at nitration, bromination, and chlorination, and in following videos, we're going to be looking at the Friedel-Crafts, alkylation, and acylation. But if you learn this mode of mechanism, then you'll be able to apply that. What we need to be able to do is specifically understand what the electrophiles look like in each of those cases and how those electrophiles are formed. So let's start with nitration first of all. So if we take a simple benzene, this is the overall product that we get, and the byproduct is water. The NO2 comes from the electrophile in this case as being NO2+, or also known as the nitronium ion. The way this electrophile is produced is through the reaction of our two reagents that we needed, nitric acid and sulfuric acid. So we know already that one of the products is going to be the nitronium ion, and basically we need two equivalents of the sulfuric acid. Concentrated sulfuric acid is the stronger acid, so it's going to donate its hydrogens to here. with each of these sulfuric acids donating a hydrogen plus ion each, we get the byproduct, which is this anion here. Those 2 moles of H plus go with the nitric acid to form this species. You don't need to remember this in grey, but it just helps you understand where it's come from. Then this breaks down into the nitronium ion that you can see up in the equation here, and also H3O plus. And so that is our last part of this equation. It's then worth noting that this can react with this to form our water, and then also it regenerates sulfuric acid. So the H plus has come from the hydroxonium ion, the H3O plus, and obviously this has come from this ion here, and they recombine to form sulfuric acid. So it's catalytic because you've used some up but reforming it in this step. So do memorize this because you could be asked to show the regeneration of a catalyst in the exam. Now this is the equation that you need to know for the exam boards for A-level chemistry. You don't need to understand this or the science behind it. You can literally memorize this, and that allows you to understand how the electrophile is generated, and then you can plug on with this generic electrophilic substitution mechanism. Now we're going to turn our attention to chlorination. So our electrophile in this case is going to need to allow us to add chlorine. So this is the Cl+, and this electrophile is generated from the reaction of the halogen chlorine with the halogen carrier. Now the aluminium trichloride here, and again in grey, you don't need to know this, but it might help you understand and therefore remember, is electron deficient. So this aluminium wants electrons, and there's electrons contained in this covalent bond. So what happens is we break this bond, and these electrons move to here, forming a new bond between this chlorine and the aluminium, as shown here. And you can see that this chlorine now doesn't have enough electrons around it, and so that forms a positive chlorine, which is our electrophile. So you may be asked to recall this equation for the generation of the electrophile, and so you've got to learn this. What you might also be asked is to show that this is regenerated to form aluminium trichloride, because the halogen carrier is a catalyst. So whilst it has changed into a new form here, another step in the reaction, which is the release of this hydrogen, will react with this form to bring it back to aluminium trichloride. So this occurs by the proton, the H+, which gets released in this step, reacting with AlCl4-, and then that forms the aluminium trichloride and the byproduct HCl. So you can clearly see in these two steps the reproduction of ACl3, and it's being used up here means that we have a catalyst. If you chose iron trichloride here, you would just swap the Al for Fe, and then it would follow the same thing. Now, bromination is exactly the same, but all we need to do is substitute in the correct electrophile and the correct halogen carriers and the correct halogens. So there's our general electrophilic substitution, and then formation of the electrophile. You can see why we have to match the electrophile's halides to the halogen. Gives us Br plus the Al Br4-. This then reacts with the H plus and regenerates our Al Br3. So then again, we've got our catalyst. So it's important that you memorize these different forms of forming the electrophile, as well as this generic mechanism, and apply it just by substituting in the electrophile of choice. So now it's time to practice to see if you can recall some of the facts that we've learned so far. So my first task is to see if you can recall the reagents and conditions for each of these transformations. Second task is to see if you can show which byproducts are formed. And the most difficult task is for each of these transformations, construct the electrophilic substitution mechanism, including how the electrophile is generated, and in the cases of bromination and chlorination, how the halogen carrier is regenerated. So pause the video now and attempt those different tasks. Okay, so the answers are coming up for question 1. And remember, if you're finding this difficult to memorise, make sure you get these on a flashcard. It's really easy marks to pick up in the exam. The byproducts for question 2. And finally, the electrophilic substitution mechanisms. They all involve the following electrophiles. And we can fit this in the generic electrophilic substitution mechanism. And remember to really take care with your arrows. Ensure that this curly arrow here starts from the ring and goes out to the electrophile in this direction, and that this curly arrow starts from the bond, the carbon-hydrogen bond, and goes into the ring. And then you can see here this red box is just because it's always hydrogen, but obviously depending on the reaction that you're doing, it's coupled with either another hydrogen and oxygen, bromine, or chlorine. So that's a generic pattern to memorize. So here's the answer for the electrophile formation for the nitronium ion. So remembering this equation. And then for the halogen positive electrophiles, then they both follow this format. So we've formed the electrophile here, whether it be bromine or chlorine electrophile. And then also we need to show that the halogen carrier, this one, the aluminium trihalide, is reformed. So it reacts with the H plus and gives us our byproduct, the hydrogen halide. So the difficulty with exam questions in aromatic chemistry is that they are very synoptic and tend to draw on lots of areas of aromatic chemistry, including directing groups, phenol chemistry, etc. However, there are still some questions out there that link to only this first set of ideas in aromatic chemistry, this being one of them. So pause the video now and have a go at this 2 marker. So this links back to nitration. You obviously can see that because of the reactants that we're given. And all the questions asking you to do is basically come up with the set of reactions that allow H2SO4 to be used up to generate the nitronium ion that has allowed this NO2 group to be placed here. Here we have the sulfuric acid reacting with nitric acid, produces the nitronium ion that allows for the nitration to happen. And then we have our 2 species here. Now, whilst this is perfectly acceptable in what we looked at earlier on in the video, lots of students don't like the fact that the byproduct here is water, but obviously we've got a bit more of a complicated system here. So instead, you can actually have another formula for the generation of the electrophile. So still sulfuric acid reacting with nitric acid, but the big difference is we only have 1 mole of sulfuric acid. You still form the nitronium ion. This time you form HSO4, only 1 mole of it, and just form the water molecule. Now, obviously, the sulfuric acid has been used up in this step, and what we need to do is regenerate it in order to demonstrate that it acts as a catalyst. So we're going to take this species here, and we're going to react that with the H plus ion, which is because we've got so much acid in the system. This then forms our sulfuric acid. And so we've used up sulfuric acid in either of these steps, doesn't matter which one you remember and learn for this, and we've reformed it in this second step, and therefore it's a catalyst. So in this video, what we've looked at is the electrophilic substitution of benzene. We've looked at the generic mechanism, and then we've focused in on nitration, chlorination, and bromination. In the next video, what we're going to do is start to look at the Friedel-Crafts reactions, so carbon-carbon bond-forming reactions, where we can do acylation and alkylation. If you found this video useful, please like it, and then ensure that you subscribe to the channel in order to get new videos as and when they're uploaded.